Hello everybody, my name is Nina Voronova and I work at the Theoretical Nuclear Physics Department at National Research Nuclear University MEPhI. Our department is a part of Institute for Laser and Plasma Technologies that unites physicists of different fields of expertise to move the science forward. In particular, my group within the Department of Theoretical Physics works in the field of light-matter coupling phenomena. From these words, you can guess that we are uniting light with matter and see what comes out of it in different regimes. However, another name for this field is solid-state cavity quantum electrodynamics, which sounds already much more sophisticated. Let me point out that the effects originating from light-matter coupling have stimulated the development of optics for the last 3 centuries. Nowadays, the limits of classical optics are reached in a number of solid-state systems, and quantum optics has become an important tool for understanding and interpreting modern optical experiments. Quantum optics is a field of research that uses semi-classical or quantum mechanical physics to investigate phenomena involving light and its interactions with matter at submicroscopic levels. In other words, it is quantum mechanics applied to photons and light. The rapid progress of crystal growth technology in the 20th century allows the realization of crystal microstructures that have unusual and extremely interesting optical properties. These structures are called microcavities. Microcavities are confined solid-state structures that exhibit a large variety of optical phenomena and serve as building blocks for many optoelectronic devices, such as light-emitting diodes and lasers. At the edge of research, the microcavity represents a unique platform to study quantum optics and photonics. The central objects of such studies in these systems is the exciton-polariton, a half-light, half-matter quasiparticle exhibiting very specific properties and playing a key role in a number of beautiful effects, including parametric scattering, solid-state Bose-Einstein Condensation, superfluidity, superradiance, entanglement, Josephson phenomena, simulation, neural networks, and so on. At present, hundreds of research groups throughout the world work on fabrication, spectroscopy, theory, and applications of microcavity exciton-polaritons. The progress in this interdisciplinary field at the interface between optics and solid state is extremely rapid. In this short lecture, I will introduce microcavity exciton-polaritons and tell you about the research of our group in the field of light-matter coupling that we carry out at the Theoretical Physics Department of the Institute for Laser and Plasma Technologies of National Research Nuclear University MEPhI. Let's switch to the presentation. First of all, let me introduce the team which works on light-matter coupling at Theoretical Physics Department. It is Professor Yuri Lozovik, myself, 2 master students, Anna Grudinina and Stanislav Subotin, and a PhD student, Maxim Posazhenkov. The topics which we are working on include excitons, exciton-polaritons, Bose-Einstein Condensation and superfluidity, novel 2-dimensional materials, Josephson phenomena, and superconductivity. Before I describe the system, I will use a very nice animation video made by the University of Sheffield to introduce to you what an exciton is and what are microcavity exciton-polaritons. In this video, we will discuss how polaritons acquire their remarkable properties. Think about a guitar. This is a simple mechanical resonator. When the string is hit, it starts to oscillate and produces sound waves with a characteristic frequency. These resonant frequencies, as they are called, are the ones for which exactly a whole number of oscillations fit between the fixed point of a string. For waves with other frequencies, the string tries to move at the points where it is clamped down, and the waves quickly become very weak. Only waves of resonant frequencies can survive on the string. Just like the sound wave on a guitar string, light can also be thought of as a wave. Each color of light has a different frequency. And every frequency corresponds to a different wavelength, which is the distance between the neighboring peaks of the wave. Visible light has wavelengths ranging from 450 to 700 nanometers, a size smaller than 1,000th fraction of a millimeter. Now imagine 2 parallel mirrors facing each other. This is an optical resonator. It confines light inside by making it bounce between the mirrors. The light waves are trapped in a similar way as the sound waves on a guitar string being trapped between the two clamps. As a result, only some frequencies will be resonant and will be able to survive between the mirrors. The smallest possible resonator is the one where only half of the wave fits between the mirrors. The wavelength of light is less than a micrometer, so the optical resonator that confines less than several wavelengths of visible light is therefore called a microresonator. To make polariton, one needs to add something to the light. In between the mirrors, we place a quantum well, which is only a few tenths of atoms thick. It is called a well because it traps electrons in its plane so that they cannot escape to the surrounding regions. If a light wave with the right frequency passes through a quantum well, it can give up its energy to release the electron from the atom it is bound in, creating a vacancy. Relative to the surroundings, this vacancy is positively charged and is called a hole. Since the electron and the hole have opposite charges, they attract and for a while orbit around each other. This behavior forms a new particle, which is called an exciton. Eventually, the exciton recombines when the electron falls back into the hole. The energy is released as a light wave with the same frequency as the one which is originally created the exciton. The quantum well is then placed in the plane that intersects with the peak of the light wave. So when the microresonator is calibrated so that the resonant light wave and the exciton have the same energy, a single exciton can be converted into a light wave, which then converts into an exciton, and so on. The resonant optical cavity traps the light wave emitted by the exciton so that it returns and creates another exciton, which also decays. A repeating cycle between the light wave and an exciton is made possible. Since the exciton and light are constantly interchanging, they behave overall as a new quasiparticle, which is called a polariton, which has some properties of each. Now let's put what we have just seen on mathematical grounds. Light confined inside an optical resonator. Here it is a Fabry-Perot resonator where mirrors are made of many dielectric layers that, due to destructive interference for transmitted waves, confine the light wave inside the planar cavity. The boundary conditions can be written as having an integer number of half wavelengths equal to the cavity width A. Since the wavelength is connected to the wave vector as 2 pi over kz, we see that the z component of the wave vector of light becomes quantized. As a result, the dispersion law for photons, which is usually E equal h bar kc, in the region of low in-plane wave vectors can be expanded in Taylor series, which results in the parabolic law. This means effectively that the photons inside such a resonator become two-dimensional and acquire an effective mass. Since the z projection of k is fixed, the in-plane wave vector corresponds to the angle at which we inject the light inside the resonator. Thus, we can plot this parabola both against the wave vector and against the angle with respect to the normal direction to the cavity layers. Now, let's place a quantum well, one or a few, inside the microresonator. Excitons are confined to the quantum well plane, and therefore they are also two-dimensional. We see that their energy dispersion has the same shape. However, the exciton mass inside the semiconductor is a few orders of magnitude larger than that of a photon. So the exciton parabola on the same graph looks basically as a flat line. From this graph, we see immediately that there are regions at which we have a crossing of two different particle dispersion, which means that at the same k and same energy, two different modes exist at the same time. In quantum mechanical language, it means that these energies are degenerate. However, since photons and excitons don't just coexist, but they interact, or we say couple to each other, this light-matter coupling lifts the degeneracy, and instead of a crossing of two dispersions, one gets an avoided crossing and the two new branches of energy. These branches correspond to the new quasiparticles that are formed inside the microcavity, the upper and the lower exciton-polaritons. Their new dispersion laws are given in the blue box, and they depend on the detuning between the photon and exciton branches and the so-called Rabi splitting energy, the energy splitting between the new polariton branches at the point of the resonance. At zero in-plane momentum, the separation between the upper and the lower Polariton energies is the mean square of the two. The laser pump, being shined at any angle, allows to probe the Polariton dispersion at any k. Since the mirrors are not perfect, sooner or later the photon will leave the cavity, and thus the lifetime of the Polariton quasiparticle is relatively short. On the other hand, the photons emitted by the cavity carry all information about the system inside, and thus allow the experimentalists to obtain the information on both momentum and coordinate distribution of the polaritons. Therefore, we can observe all the phenomena happening inside without actually destroying the system. Let's summarize. Polaritons are the new modes of an optical microresonator, which appear in the so-called strong coupling regime, when the radii-splitting energy is larger than the line width of the branches. They are directly accessible both for injection and detection by shining light on the cavity. The new dispersion laws are much different from those of cavity two-dimensional photon and the quantum well exciton, and thus the allowed frequencies inside the resonator are just a few. Polaritons inherit from their photon component an extremely light mass. It is of the order of 10 to the 5 of the free electron mass. On the other hand, due to the exciton component, they interact because excitons are complexes of electrons and holes which display electrostatic interaction. At that, the new quasiparticles are bosons, which means that they have integer spin. Bosons are known for their ability to macroscopically occupy a single quantum state, a phenomenon which is called Bose-Einstein Condensation. Compared to the system of cold atoms, which were first where the DEC has been observed, polaritons, since their effective mass is orders of magnitude smaller than that of an atom, are expected to condense at temperature much higher, up to room temperatures. This is because the critical temperature of transition into the macroscopically coherent state is inversely proportional to mass. In addition to that, this is what a typical setup for atomic BEC looks like. And this is an optical table on which typical exciton-Polariton condensation experiments are carried out. The mechanism of Polariton-Bose condensation can be different. Under the resonant pump, the panel on the right, one directly excites the so-called inflection point on the Polariton dispersion, and then polaritons scatter with each other given the energy and momentum conservation laws, and end up at k equal to 0 in the so-called idler state, which is a point higher at the dispersion. Another way, which is shown on the left graph, is to excite the system non-resonantly at energies much higher, where the lower Polariton branch basically coincides with the exciton dispersion law. From there again, polaritons scatter down along the lower Polariton branch, eventually ending up at the state k equal to 0. As soon as some considerable number of particles has reached the lowest state, the effect of bosonic stimulations kicks in when the probability of transition to the final quantum state is proportional to the square root of the number of particles already in the state. This way, a macroscopically large number of polaritons is accumulated at the bottom of the Polariton dispersion, which means that the condensate is formed. Photons that eventually leave the resonator when the polaritons decay inherit all the properties of the condensate from where they originated. They are coherent, monochromatic, polarized, and unidirectional. All these properties correspond to laser light. And what I have just now introduced is the concept of a Polariton laser, a device that emits coherent light without any population inversion. Next slide shows several experimental works from different groups around the world that have achieved exciton-Polariton condensation in different material systems. What I mean by materials here is the dielectrics or dielectric layers from which the cavity reflectors and the quantum wells that host excitons are made. Typical systems are gallium arsenide, cadmium telluride, gallium nitride, and zinc oxide. As you see, temperatures at which the condensation has been observed are really high, up to room temperatures. The signatures of reaching Bose condensed phase is the narrowing and the great intensity increase of the emission peak, which corresponds to most particles accumulating at a state with k equal to 0, which corresponds to the photon emission in the normal direction. On the next slide, I present a compilation of just a few relevant experimental works in which many beautiful phenomena with exciton-polaritons and their collective excitations are observed, such as Polariton BC in traps, Polariton superfluidity, vortices and solitons in the Polariton fluid. After this detailed introduction, let me focus more on the applications. As such, there are works on Polariton laser with vertical injection, where the excitons are created in the quantum well electrically by placing an electrode on top of the cavity and applying bias. Again, you see here on the right-hand side the typical picture for Polariton condensation, the narrowing or the dispersion into the single state occupation. Next is Polariton laser with horizontal injection, where the electrodes are placed on both sides of the cavity in lateral direction. The middle panel shows what the actually fabricated system looks like. It is a microscope image of the device. Right graph on the right-hand side shows another typical feature of Bose-Einstein condensation. It is the drop of the line width at the threshold, which is shown as a blue line, and the blue shift of the energy given by the red line, which happens due to the interaction of the macroscopic number of particles accumulating in the same state. The term blue shift means that the energy of the state shifts up towards the higher frequencies, or in the language of the wavelength, towards the blue part of the spectrum. These two examples of Polariton lasers with electrical injection show that the device can actually be useful as a source of the coherent light. The argument here is that if you use just optical excitation and not electrical, you'd always need a laser to inject photons inside the resonator and consequently create a Polariton laser. But using a laser to create a laser is a debatable concept. Next type of the device that can be made of Polaritons is the source of terahertz radiation. Terahertz range of wavelength lies in between far infrared and microwave radiation in the electromagnetic spectrum, and emitters of coherent terahertz radiation to date are not really developed. Using the Polariton system, it was suggested to create a so-called bosonic cascade laser, which would emit both in the visible, along the direction normal to the resonator, and in the terahertz range, in the in-plane direction. The idea behind this device is to confine excitons in a parabolic quantum well, which would make Polaritons occupy equispaced energy levels similar to those of a quantum harmonic oscillator. Exciting the system at a higher level and letting it go down to the lowest state, having in mind the effect of bosonic stimulation, the more particles go down, the higher the probability for the rest to go down. One achieves a cascaded process in which terahertz photons corresponding to the energy difference between the levels are emitted. This idea is purely theoretical, and it is patented by a Russian group in St. Petersburg State University. Another property of Polaritons is them carrying a spin. Excitons that couple to light have total spin equal 1, since it is a composition of an electron and a hole, both with spin 1/2. Polaritons, therefore, can be excited with a defined spin if we use the photons with a defined left or right circular polarization, or with different spin textures forming inside the microcavity. This gives rise to the field of spintronics compared to electronics, a branch of science where electrons are replaced with particles carrying spin, and that allows to observe even the so-called spin superconductivity, the spreading of a defined spin without dissipation. By making systems with certain geometries, microwires of a special shape, where light is confined not only in z direction, but also along either x or y, one can observe this spreading of spin domains along the cables, which allows to think of replicating neural networks with Polaritons. Next slide shows a Polariton lattice, a system where the Polariton condensate is formed not just in one spot, but in a set of spots forming an ordered structure. Such lattices allow the realization of quantum annealing algorithm, which is making a system evolve and reach the ground state of a potential landscape. Programming certain potentials into the system by imposing different interactions between the different sides of the system, one implements the concept of a Polariton simulator, an algorithm that solves mathematical problems faster than a supercomputer and way cheaper than a D-wave machine, which is based on superconducting qubits. As a conclusion, I show an overview of the field of light-matter coupling and exciton-polaritons in particular. This system is very rich both for fundamental effects and applications. Both on the experimental and theory side, there are many unique solid-state phenomena to study, such as BSC, superfluidity, bosonic Josephson effect, spin-related phenomena, topological defects like vortices and solitons, quantum correlations, and so on and so forth. And this is what we are dealing with in our group. At the end of this introductory lecture, let me show you a map which indicates just a few places that conduct leading research in the whole world in the field of exciton-polaritons. This is Spain, France, USA, Switzerland, Germany, the United Kingdom, and of course Singapore, Japan, and Russia. With this, I thank you for your attention.